In this module, we will discuss colligative properties of solutions. To understand the concept of colligative properties, consider an ideal diluted solution. Such solutions exhibit the ideal behavior of solvent A. The ideal behavior of the solvent means that its chemical potential in the solution can be represented by this equation. Here, μAl represents the chemical potential of solvent A in the solution. μAl star is the chemical potential of solvent A in its pure liquid state. Xa is the mole fraction of solvent A in the solution. Interestingly, the chemical potential of the solvent does not depend on the type of solute present. Instead, it only depends on the mole fraction of solvent A and therefore on the total mole fraction of all solutes. This phenomenon leads us to the term colligative properties. These properties are characterized by the dependence solely on the amount of solute particles present in the solution rather than their chemical identity. From this equation, we understand that the chemical potential of the solvent in the solution is reduced from its value for the pure solvent in the presence of a solute or solutes. Mathematically, this is indicated by the term which includes the logarithms of the solvent's mole fraction. The smaller Xa, the more negative this term becomes. Importantly, all the colligative properties that we will discuss originate from the reduction of the chemical potential of the liquid solvent as a result of the presence of solutes. The physical quantity of molality B is widely used to characterize the amount of solute in solutions when describing colligative properties. It is defined as the number of moles of solute B per kilogram of solvent. The mole fraction of component B can be related to molality using this equation. For the diluted solutions considered in this module, the mole fraction and molality are substantially small. Then, the mole fraction of a solute B can be approximated as a product of its molality and the molar mass of the solvent. These formulas are also valid for the total amount of all solutes if multiple substances are dissolved in the solution. For the sake of simplification, we will conduct further discussion as if there is only one type of solute. To emphasize the nature of colligative properties, we start with a few assumptions about the solute in the solution. The solute is non-volatile, meaning that it does not enter the gas phase. This is crucial as it ensures that when the solution is in equilibrium with its vapor, only the solvent contributes to the vapor pressure. Except for the vapor pressure reduction as described by Raoult's law, there are no solute effects on the gaseous phase of the solvent. We also assume that the solute does not incorporate into the solid phase of the solvent. When the solvent freezes, only pure solid solvent crystallizes out, devoid of any solute particles. This typically happens because the solute cannot fit seamlessly into the crystal lattice of the freezing solvent. Therefore, the chemical potential of the solvent's solid phase is not affected by the solute. Now we will take a look at a figure illustrating the influence of solutes on the phase transitions of the solvent. To understand this phenomena qualitatively, you hardly need anything more than this diagram. This figure shows the temperature dependence of the chemical potential for three phases of a pure substance: solid, liquid, and gas. Each line's slope represents the molar entropy of the phase. Notably, the solid phase exhibits the smallest negative slope, the liquid phase presents an intermediate slope, and the gas phase has the steepest slope. At certain temperatures, the chemical potentials of two phases become equal, defining the phase transition points, the melting and boiling point. Now, let's introduce a solute to the pure solvent. The presence of a solute affects the chemical potential of the liquid phase, causing it to decrease. What does this shift in the liquid phase's chemical potential imply for the phase transitions? The intersection of curves for the solid and liquid phases now occurs at a lower temperature due to the added solute. This is referred to as freezing point depression. On the other end, we have the boiling point. The intersection point of the liquid and gaseous phase curves shifts to a higher temperature. This phenomenon is known as boiling point elevation. Now, let us move on to the quantitative description. We start with the boiling point elevation phenomenon. When a solute is introduced into a solvent, the boiling point of the resulting solution differs from that of pure solvent. We represent the boiling point of the solution by T, which differs from the boiling point of the pure solvent, T star. This difference arises due to an equilibrium that is established between the solvent in its gas phase and in the solution. At this equilibrium, the chemical potential of the solvent in the gas phase is the same as the chemical potential of the solvent in the solution. From the above, the natural logarithm of the mole fraction of solvent Xa can be expressed in terms of Gibbs energy of vaporization, that means in terms of enthalpy and entropy of vaporization. After some mathematical transformations and taking into account that the concentration of solute is small, we arrive at this expression. It gives the mole fraction of the solute required to change the boiling point of the solvent to a new value. As we introduced previously, when a solute is added to a solvent, it leads to an increase in the boiling point of the solution. This elevation, denoted by delta T, is the difference between the new boiling point T and the boiling point of the pure solvent T star. Quantitatively, the elevation delta T is related to the molar fraction of the solute Xb by this equation. Because this equation makes no reference to the identity of the solute, only to its amount, it follows that the elevation of boiling point is a colligative property. Normally, this relationship is expressed in terms of molality B of the solute in the solution. Considering that it doesn't matter which solute is dissolved, one often talks about just the molality of the solution. It shows that the boiling point elevation is directly proportional to the molality of the solution. Let's now introduce the ebullioscopic constant Ke, which essentially encapsulates all the solvent-specific factors affecting the boiling point elevation. It is defined as follows. What's noteworthy here is that Ke only depends on properties of the solvent, such as its molar mass, boiling point of the pure solvent, and the enthalpy of vaporization. With this constant, the expression for boiling point elevation simplifies to the product of the ebullioscopic constant of the solvent and molality of the solution. Freezing point depression refers to the phenomena where the freezing point of a solution is lower than that of the pure solvent. This effect is observed when a solute is introduced to the solvent. The degree to which the freezing point is depressed, denoted by delta T, is the difference between the freezing point of the pure solvent T star and the freezing point of the solution T. The magnitude of this freezing point depression is directly related to the molarity of the solution, as shown here. Here, delta fuse H is the enthalpy of fusion of the solvent, and T star is the freezing point of the pure liquid solvent. To simplify the representation, the cryoscopic constant Kc is introduced. This constant encapsulates all the solvent-specific factors that influence the freezing point depression. Similar to the ebullioscopic constant we discussed earlier, Kc depends solely on the properties of the solvent and not on the nature of the solute. This indicates that freezing point depression, like boiling point elevation, is a colligative property. Osmosis refers to the spontaneous movement of a pure solvent through a semi-permeable membrane into a solution. This phenomenon is visualized in this figure. It shows a tube sealed at one end and containing a solution with solute particles that cannot pass through a specific type of membrane. There are some types of membranes that permit the flow of small molecules, such as water, but restrict the movement of larger molecules, such as sucrose. The tube is immersed in a beaker filled with pure solvent. As the experiment proceeds, the solvent molecules move into the tube through the semi-permeable membrane and dilute the solution inside. This process continues until equilibrium is reached. At this point, there is a noticeable rise in the solution level inside the tube, indicating an increase in pressure within the solution as compared to the surrounding solvent. This increase in pressure resulting from the movement of solvent into the solution is termed the osmotic pressure and is denoted by the capital Greek letter pi. Osmotic pressure is a key term associated with osmosis. It is the extra pressure required to be applied to the solution to stop the flow of solvent molecules through the membrane. At equilibrium, the osmotic pressure is equal to the hydrostatic pressure difference across the membrane. This equilibrium state ensures that there are no net flow of solvent and the concentrations remain unchanged on both sides of the membrane. Osmosis plays a crucial role in numerous biological processes, medical technologies, technological applications, and analytical methods. Osmotic pressure is a fascinating property arising due to the difference in the chemical potential between a pure solvent and a solution. Let's try to understand this phenomenon from a thermodynamic perspective, as visualized by this figure. In the figure, on the left side, we have pure solvent A at pressure P. Its chemical potential is denoted by mu A star. On the right side, which is the solution, the presence of solute decreases the chemical potential of the solvent. But this is counteracted by an increased pressure leading to an increase of the chemical potential. At equilibrium, the chemical potentials on both sides of the semi-permeable membrane must equal each other. This expression describes the chemical potential of the solvent in the solution. In comparison with the pure solvent, the presence of solute reduces the chemical potential of the solvent as given by the term RT times the natural logarithm of XA. On the other hand, the chemical potential of the solvent is raised when there is pressure applied to it. This contribution to the chemical potential is equal to the product of the solvent's molar volume and the additional pressure P. Now, in dilute solutions, where the mole fraction of solute Xb is much smaller than 1, we can approximate the natural logarithm of 1 minus Xbs minus Xb. Inserting this substitution into the equation above gives us this expression. From this equation, we can derive an expression for osmotic pressure in terms of the mole fraction of the solute. It is given by pi equals RT over Vm times the mole fraction of solute Xb. The mole fraction of solute Xb is approximately equal to the amount of substance of B divided by the amount of substance of A. We recognize Na times Vm as the total volume of the solvent V and the ratio of Nb to V as the molar concentration of the solute B. This is known as the Van 't Hoff equation for the osmotic pressure. It is striking that this final Van 't Hoff equation resembles the ideal gas law, illustrating the similarity between osmotic pressure in solutions and gas pressure in an ideal gas.